We're now going to take a look at something known as the antiderivative of a function. So far what we've been doing is we've been taking some sort of function and finding its derivative. What we'd like to be able to do is have a function that we know is the derivative of some other function and be able to figure out what function it is the derivative of. In other words, we want to be able to work backwards. So the process of reversing a differentiation is just called antidifferentiation. And of course, the function that we get from going through this process is called the antiderivative. Now, this isn't the only thing we're going to call this process in this function. We also can say that the process of reversing a differentiation is called an integration. And the process of reversing this and getting the function that we get from that process is going to be called an integral. So these things over here are the processes themselves, and these things over here are what we're calling the function we get from doing those things. So what is the antiderivative then from a more formal definition standpoint? All right, suppose we've got some function big f of x and little f of x, and these are two functions such that little f of x is the derivative of f of x, big f of x. So in other words, big F prime of x equals little f of x. Then we say that big F of x is the antiderivative of f of x. So ways we can go ahead and verify this. Say we've got some function big f of x which is 2x squared minus 5x. We want to verify that this is the antiderivative of 4x minus 5. So how do we do that? Well, what we do is we take the derivative of f prime of x, this big F of x, take its derivative, and so if we have 2x squared minus 5x, the derivative of that will be 2 times 2, so 4, x to the 2 minus 1, so 4x, minus the derivative of 5x, which is just 5, so 4x minus 5. So since the derivative is equal to this function, this could be the antiderivative for this function. I say could be because it turns out that there's more than one function whose derivative could be this. So if I've got some other big f of x, which is 2x squared minus 5x plus 3, and I take the derivative of that, the derivative of 2x squared is again 4x minus 5x, and take the derivative of that is minus 5, and then the derivative of 3 is 0, so 4x minus 5. So again, same thing, could be the antiderivative of this little f of x. We could also have that 2x squared minus 5x minus 1 could be the antiderivative of this function, because again, the derivative of this will just be 4x minus 5. And again, if we take the derivative of something else, say it's some constant, we don't know what the constant is, we'll call it c. Then the derivative of this will be 4x minus 5, and if it's just some constant c and there's no x, the c will come 0. So no matter, there are a number of different big f of x's whose derivative could be 4x minus 5. So what we're noticing here is that just because when we take the derivative of the function we get something unique, if we take the antiderivative, that doesn't necessarily give us one unique answer. So when the derivative process is reversed, you don't get a unique answer. Okay, so if we can't get a unique answer, does that mean there's no hope in trying to find the antiderivative? Are we done? Should we pack it up? Calculus is over. It's canceled. Go home? No, I don't think so. Because we can still find the antiderivative for the most part, we just don't know what that constant is going to be. So it's only going to differ by some constant, and we're going to call this constant C. So what we know is that a derivative function has infinitely many antiderivatives. And we call them a family of antiderivatives. They're like the Brady Bunch. Okay, they're not really like the Brady Bunch, but that's the only family that came to mind immediately. So we'll go with it. They're like the Brady Bunch. So let's say we wanted to find the most general antiderivative of each of the following functions. What we know is that we have to figure out, how we have this entire family of functions, since there could be some constant that was added on each time. So essentially what we'll do is we'll just take every single function we have and we take the antiderivative of it and add c. So when we have this f of x equals sine of x, what we're saying is what function is sine of x the derivative of? And if you'll recall, if you have sine of x, the derivative of sine is cosine of x. The derivative of cosine is negative sine of x. The derivative of negative sine will give you negative cosine of x. And the derivative of negative cosine is sine. So when you want to anti-differentiate, so this is the derivative. Going the other way will give you the antiderivative. So negative cosine is the derivative of sine, so negative sine is the antiderivative of negative cosine. Cosine is the antiderivative of negative sine, because the derivative of cosine is negative sine. Sine is the antiderivative of cosine, because the derivative of sine is cosine. And last but not least, the antiderivative of sine is negative cosine, because the derivative of negative cosine is sine. So at the end of the day, that means that our big F of x, the antiderivative here will be negative cosine of x plus c. And the reason we have to add this plus c is that this makes it the most general antiderivative. Because we know there could be some sort of constant added to it, but without a little bit more information, we can't figure out exactly what that constant would be. It'd be nice. Wouldn't it be nice if we could find the constant out? That'll be something maybe we look at later this video. So let's say we have 3x squared, and we wanted to figure out what function that was the derivative of. Well, typically when we're doing power rule, we say to ourselves that if f of x equals x to the n times some constant, then the derivative of that will be n times a, if a is the constant, times x to the n minus 1. Which would mean that that would be our little f of x. And so if we wanted to be able to go backwards, what we would do is we would go ahead and divide. We would add 1 to the power and then divide by what that new power is. So if we think about trying to do this process backwards, what we'll do is we will take and add 1 to the exponent and then divide by 3. So we will take and make big F of x equal to x cubed plus some constant. Again, we want to add this constant so we have the most general antiderivative we could think of. So if we have 3x squared, we'll add 1 to the power, so it'll be x cubed, and then divide by 3 to complete our undoing of the power rule. If we just had f of x equals x squared, again, we'll add 1 to the exponent. So I will add 1 to the exponent and then divide by the new exponent. So that means that big F of x will be x cubed over 3 plus c. All right, now what if we had something like x to the negative 3? Well, here again, we're just going to use power rule, but backwards. So we'll add 1 to the exponent and then divide by the new exponent. So big F of x will be x to the negative 2 divided by negative 2 plus c. Or you could think of this as being negative 1 over 2x squared plus c. Either way would be perfectly fine. All right, so then let's talk about, in general, what's going on with some of our antidifferentiation formulas. So say we've got a function that looks like x to the n, and n is not equal to negative 1. One day we'll talk about why n is not equal to negative 1 is a big deal, but what we'll have is x to the n plus 1 divided by n plus 1 as the antiderivative, as we've seen up until this point. And this would be plus something. So right, so we should be adding plus c to all of these if we want the general form of them. Say we've got some constant, it says c here, I'm going to change that to little a. So if we had a times f of x, then a times big F of x will be the antiderivative. Basically, if we multiply some function by a constant, that constant that's being multiplied out front isn't going to change in general what the antiderivative should be. If we have two functions being added together and we want to take their antiderivatives, then the antiderivative we'll get will just be if we had taken the antiderivatives separately and added them together. Going for some of these more particular things with sine and cosine, say we had cosine, its antiderivative is sine of x. Say we had sine, its antiderivative is negative cosine of x. Again, you'll probably want to refer to this little chart up here about sines and cosines. Secant squared, remember that we take the derivative of tangent to get secant squared, so that'll be tangent of x. And secant squared, or secant x tan x, will be just secant of x. So remember, the derivative of secant is secant tangent. So it'll come down to what function do I take the derivative of in order to get this function. All right, let's see a few more examples. Say we wanted to go ahead and find all functions g such that g prime of x equaled 4 sine of x plus 2x to the fifth minus the square root of x all divided by x. So here we want to simplify this as much as possible first. We don't have a reverse quotient rule yet. In fact, we'll have kind of more ugly things. So how we have product rule, chain rule, quotient rule, We'll have some things we can do to try to take more complicated antiderivatives, but for now we don't have any of that. So what we're going to do is we're going to simplify this as much as we can. So g prime of x is going to be the same as 4 sine of x plus 2x to the 5th over x minus x to the 1/2 over x, which we can also think about as being 4 sine of x plus 2x to the 4th minus x to the negative 1/2. Now when we go ahead and take the antiderivative of this, we'll take the antiderivative piecewise. So the antiderivative of sine of x is negative cosine of x. So multiplied by 4, that'll be negative 4 cosine of x, plus the antiderivative of 2x to the 4th will be 2x to the 5th over 5. So just the antiderivative of x to the 4th is x to the 5th over 5, and then multiplied by 2, and then minus negative 1/2 plus 1 will be 1/2, so this will be minus x to the 1/2 divided by the new exponent, which is 1/2. And then we have to remember to add our little constant, so plus c. So if we go ahead and simplify this, dividing by 1/2 a little bit more, we get that g of x will equal negative 4 cosine of x plus 2/5 x to the 5th minus 2 square root of x plus c. So square root of x, just x to the 1/2. All right, so we've got that antiderivative. Now let's say we wanted to go ahead and look at another function. So say we want to find the function f if f prime of x equals x times the square root of x and f of 1 equals 2. So earlier how I said we don't necessarily know what's going on with this constant, now we have something that we could try to use to figure out what the particular antiderivative is, the specific antiderivative we're looking for. So say this was our function, our derivative, f prime of x equals x times the square root of x. This is the same as x to the first times x to the 1/2. When you're multiplying x's like this, you'll go ahead and add the exponent, so this will be x to the 3/2. And if we want to take the antiderivative, we'll just add 1 and divide by the new exponent. So f of x then would be x to the 5/2 divided by 5/2 plus c, or in other words, it would be 2/5 x to the 5/2 plus c. Now we know that f of 1 equals 2. So taking this information and this information and putting them together, what that means then is that 2, which would be f of 1, would be equal to 2/5 times 1, the x, to the 5/2 plus c. Now we don't know what c is yet, but we can find out. So if we have 1 to the 5/2, that'll just be 1, so we'll have 2 equals 2/5 plus c, and we can subtract 2/5 over from both sides to get that c equals 8/5. So that means that our original function f of x would be 2/5 x to the 5/2 plus 8/5. So if we're given some sort of initial condition, we can go ahead and figure out the specific derivative, or the specific function that we have the derivative of. We get a specific antiderivative. All right, so say we've got the graph of some function, and we would like to know what its antiderivative would look like. So I'm going to make a little bit of a quick sketch over here. Kind of start at 0. We got 1, 2, 3, 4, and 5. We try to line that up a little bit better with the graph above. 3, 2. Okay, so what do we know about this function? We know that if we have a function, I confused O and N there for a second. If we have a function that is increasing, its derivative is going to be positive. And if we have a function that's decreasing, its derivative is going to be negative. Now, if we have a horizontal tangent line, that'll happen when the derivative equals 0. So what does that mean for us? Well, what it means is that we have the graph of the derivative. So this is the derivative. So the original function is going to be increasing on 1 to 3 because the derivative is positive. So derivative is positive on 1 to 3, which tells us that big F of x is increasing on 1 to 3. And since the derivative is negative on 0 to 1 and on 3 to infinity, our original function is decreasing on 0 to 1 and 3 to infinity. So it just keeps going. And then, since we know that the derivative equals 0 at x equals 1 and 3, that tells us that big F of x has horizontal tangent lines at x equals 1 and 3. Alright, so we'll, again, because our original function is going to be a family of functions, we don't actually know what the y-intercept is, we don't know what that constant c is, we have to just kind of pick something. So we'll start off here. Now we know that between 0 and 1, we should be decreasing. So we should go something like this. So we get to a point where we get to 1, and then we stop. Now at this point we should have a horizontal tangent line with our function, so we shouldn't be increasing or decreasing at that point. Now between 1 and 3, we should be increasing. So we should be going up. And then once we get to 3, we'll again have another horizontal tangent line to stop at. Now once we get to this point, we're decreasing the rest of the way. So from 3 to infinity, we want to make sure that our function is decreasing. And then it keeps going. Now this is about as far as we can do without having more specific information. If we knew exactly what the function f of x was, we might be able to know exactly what the y values should be here. We might be able to figure out if we had an initial condition, what the y-intercept is. But this is all we have for now. So this is kind of a sketch of what we could expect the antiderivative of this function to be. All right, let's go through 2 more examples just to make sure we're understanding what's going on. So let's say we've got a particle, and the particle is moving in a straight line and has an acceleration given by a of t equals 6t plus 4. Its initial velocity is v of 0, which is negative 6 centimeters per second, and its initial displacement is s sub 0, which is 9 centimeters. We want to find the original position function t. So again, we want to kind of remember that when we're talking about examples like this, we've got some derivatives to keep in mind. So we start off with position, and position is this s of t. Sometimes it's p of t. But from position we go to velocity, and the velocity is v of t, which is little s prime of t. And the derivative of velocity is acceleration. Acceleration is a of t, which is the derivative of velocity, which is the second derivative of the position. So with this little reminder over here on the side, what we want to do is we want to go ahead and find out what the initial function was. So we know that a of t equals 6t plus 4. And when we're looking at this, we can think of this as being 4 times t to the 0. If we have some sort of constant, then when we take the antiderivative of it, we should be multiplying it by t. So we've got then v of t. This is the antiderivative for the acceleration. That'll be the velocity. So we go from acceleration to velocity, and eventually we'll go to position. But right now we're stopping at velocity. So the antiderivative of this will be 6t squared over 2. So added 1 to the exponent here of 1, and then divided by the new exponent, plus 4 times t to the first over 1, which if we're dividing by 1, it's just going to be the same thing, plus c. And so this is the same as 3t squared plus 4t plus c. Now we know that v of 0 equals negative 6, which tells us then if we set this equal to negative 6 and plug in zeros for t's, we should be able to figure out what c is. So this means that we have 3 times 0 squared plus 4 times 0 plus c equals negative 6. But at the end of the day, well, that'll tell us is that c is equal to negative 6, because it'll be c plus 0 plus 0. So that's going to help us out. That means that velocity is going to be 3t squared plus 4t minus 6. And then from here, we'll be looking at the antiderivative of this function to get our position function, s of t. So s of t will be the antiderivative of this function, so that'll be 3t cubed over 3 plus 4t squared over 2 minus 6t plus d. So you might be wondering, well, why is Mr. Smith using d instead of c? Well, the only reason I'm using d instead of c, it is just some arbitrary constant that we have to keep in mind we'll have here. But I already used c, so I just want to make sure I don't get myself confused. If you know how to keep them separate, that's fine. You could use c here again, but it might lead to some confusion. So this is the general antiderivative. We want the specific antiderivative here. So we want to know what the initial position function is. So we know that s of 0 equals 9, which is going to tell us that 9 equals, we could simplify this a little more. This will be t cubed plus 2t squared minus 6t plus d. And when we do that, we'll get 9 equals 0 cubed plus 2 times 0 squared minus 6 times 0 plus d, which tells us that d equals 9. And so if d equals 9, then that means that our original s of t will be t cubed plus 2t squared minus 6t plus 9. So again, because we were given some sort of extra information about what we had initially, we could do the work in order to figure out what the specific position function we had was, as opposed to having to include arbitrary constants. All right. So let's do one more example. A ball is thrown upward with a speed of 48 feet per second from the edge of a cliff 432 feet above the ground. We want to find its height above the ground t seconds later and know when it reaches its maximum height and when does it hit the ground. So something to note here, an object near the surface of the Earth is subject to a gravitational force that produces a downward acceleration denoted by g. For motion close to the ground, we can assume that g is constant at 9.8 meters per second squared, or 32 feet per second squared. So this thing that we're doing is we're trying to find the acceleration of a ball, or we have the acceleration of a ball that is due to gravity. And know that this is going to be a downward motion, so we should have some sort of negative acceleration. So all we know is that the acceleration of this ball we're saying is constant at negative 32 feet per second squared. We want to find out when it reaches its maximum height, which means we would need to know the position of it, and we need to know when it hits the ground, so when it's going to be 0. So if we want the velocity, that'll be the antiderivative of negative 32. So that'll be negative 32t plus our constant c. We know that we are thrown upward with a speed of 48 feet per second. We are thrown upward with a speed of 48 feet per second. So this tells us that v of 0 equals 48. And so using this with v of 0 equals 48, that tells us that 48 equals negative 32 times 0 plus c. So c is 48. So that means our v of t is negative 32t plus 48. Now from here we want to go ahead and find our position function. So we know that the position function will be the antiderivative of velocity, so that'll be negative 32t squared over 2 plus 48t plus d, or again, negative 16t squared plus 48t plus d. Now we also know that when it's thrown, it's from the edge of a cliff 432 feet above the ground. So that tells us that our initial position when t is 0 is 432. So if we use that, and we see that s of 0 equals 432, what that tells us then is that 432 equals negative 16t times 0 squared plus 48 times 0 plus d. So that tells us then that d equals 432 for that initial position. And so that means that s of t, which will answer part of what we need, our position is going to be negative 16t squared plus 48t plus 432. So this will help us figure out the position or the height above the ground t seconds later. We want to know when it reaches its maximum height. What that means is for the max height, we need s prime of t to equal 0. But remember, s prime of t is just v of t. So we need v of t to equal 0. All right, well, that's easy enough. S prime of t is going to be negative 32t plus 48, and we want it to equal 0. So if we set it equal to 0, we can subtract the 32, or we can add 32t to both sides to get 48 equals 32t. Then we can divide both sides by 32, and we end up seeing that this will happen when the time equals 1.5 seconds. So if time is going to equal to 1.5 seconds, then that is when it reaches its maximum height. So we'd find the maximum height by then going ahead and doing a little bit more work. We'd go ahead and plug into our position function to find the maximum height. So this little here is an s, or it's distinguishable from the 5. That way when we're looking at the notes later, it'll make a little more sense. Now we want to know when it hits the ground. And when it hits the ground, what should happen is s of t should be equal to 0. So we want to know when that happens. So what we'll do is we'll set our position function 16t squared plus 48t plus 432 equals 0. But we'd like to be able to find the roots of this function. In other words, we want to figure out when it's going to be equal to 0. So what we'll do first is we'll factor out a negative 16, and we'll get t squared minus 3t minus 27 equals 0. So that'll help us a little bit. Now the bad news is that this doesn't factor very nicely the way we'd like it to. So we'll use the quadratic formula. Remember, we've got A, B, C. So when we're setting up this formula, we've got that t equals opposite b plus or minus the square root of b squared minus 4 times a times c, so minus 4 times 1 times 27. Sorry, negative 27. All over 2 times 1. Now when we do that, we will get 3 plus or minus the square root of 9 minus 4 times 1 times negative 27, which will be the square root of 117 divided by 2. For those playing at home, this is the square root of, or this is 3 square root of 13 over 2, just in case you wanted to factor that out a little more. And this will be our options for t. Now, something to point out is that if we take 3 minus 3 times the square root of 13 divided by 2, that'll be a negative number. So we don't want to consider the negative option here, and we'll only want to consider the positive option, because the negative option is before we throw, and that doesn't make a lot of sense for our problem. So that means that t will be equal to 3 plus 3 times the square root of 13 over 2, which means we will get roughly, let's go ahead and type this in the calculator just to be sure, 3 plus 3 times the square root of 13 divided by 2 should get roughly 6.91 seconds. So it's going to reach its maximum height after 1.5 seconds, and it'll hit the ground after about 6.91 seconds. So these are some of the fun things we're going to get to start doing with antiderivatives. In the upcoming videos, we'll be looking at more complicated antiderivatives and why we would even want to take the antiderivative of some function.